Hi everyone. We're going to talk about sampling the hypergeometric distribution. Okay, so if you recall, we had defined the hypergeometric um, using the following. So we're doing n choose k. So let's just say we're trying to draw a poker hand, right? So but what is the successes? Maybe aces, right? So what are we doing? The probability of drawing three aces is 4 choose 3. My times 48 choose 2, right? So the 48 other cards that aren't aces, choose 2 of those over 52 choose 5, right? So that's what we mean by the hypergeometric distribution, and we had written the theoretical distribution that way. Okay, and as I've just said, the typical or one major example of the hypergeometric distribution is drawing cards. Okay, how many aces are in a 5-card poker hand, or how many hearts are in a 12-card hearts hand? Okay, well, that's interesting to a point, but we need to know the expected value. So now the expected value for the number of successes in a hypergeometric distribution is n. This is the number of things that are being drawn. This is the total number of successes, and this is the total number of objects being drawn from. Okay, and that was all explained on the previous slide. So if we're looking to analyze the card game Spades, we have a 13 card hand. In a 4-player game, every player gets dealt 13 cards. Okay, and the reason the card game is called Spades is because spades are always trumps, right? So they're always the valuable cards to have. All right, and so from the previous slide, we have n equals 52, k equals 13, lowercase n, we're drawing 13 cards, and k is the number of successes, right? And we can have between 0 and 13 successes. All right, so the expected number of successes on average, right, is n, we're drawing 13 cards. Out of 13 successful objects we can draw, out of 52 total objects we can draw, right? 13 over 52 is 1/4. So we basically have 13/4 or 3.25. Okay, so that's just plugging everything in and making sure that we've mapped, all the values to the hypergeometric distribution. Okay, but if we're going to do this experiment, we need to be able to draw from a deck of cards. And that requires setting up a data frame. All right, the first step in which is we're going to create 2 data vectors. Right? One for suits and one for values. Now, we're going to use the repeat function, okay? And it's just rep, and we say the thing that we want to be repeated, and we say the number of times that need to be repeated, and this would be the output. If you do what's in blue, right, it's just going to create 4 capital X's in a data vector. All right. So to do the deck of cards, what do we need to do? Well, we're going to use repeat here, the numbers 2 to 14, and do it 4 times. Why? Well, those are the cards, 2, 3, 4, 5, 6, 7, 8, 9, 10. The 11 is a jack, the 12 is a queen, the 13 is a king, the 14 is an ace. So we have 4 of each of those values, right? So we have this data set, but they go in order. 2 through 14, and then 2 through 14, and then 2 through 14. Why? Well, because next we create the suits, and we do 13 spades, which is just the character S, and we do 13 hearts, which is just the character H, 13 diamonds, and 13 clubs, and they each have, so each of the values gets mapped exactly 1 time to the clubs, exactly 1 time to the diamonds, and so forth. So we have 2 data vectors now, the values and the suits, and we join them together into a data frame. Right, using the data frame function. So V equals values, suits equals, so what are we doing here? We're putting in these names, right? Why? So that those will be the names of the titles. Factor, what is this saying? It's saying that it's not a numeric variable, it's a category variable or a factor variable in statistics lingo. Okay, and then we've created this deck underscore DF for our deck of cards data frame. Using the $ notation, we extract the suits column and we sample 13 cards. So we're using the sample function on this data frame we created. And it's just going to tell me how many S's are drawn, for example, and I can use the sum function to count them up, right? Hand is just a 13 card data vector, and the only thing that's listed is the suits that are drawn, right? That's all we're looking at is the suits that are drawn, and then I can use the sum function to count up the number of S's. All right, and so we have this notebook, right? Sampling Hypergeometric is the name of the notebook, and this has everything laid out so that we can answer the research question. On average, how many spades will be drawn into a 13-card spades hand? All right, so we'll jump over to the so here we are in the notebook that you have linked in D2L. And here are the commands that we just went over that create the deck of cards, right? And you can see we've drawn, we're displaying the first 5 rows. And the first 5 rows are the 2, the 3, the 4, the 5, and the 6, and they're all in the spade suit just because we listed spades first, okay? And if you want, you can look at the whole data frame there. That's up to you, but you can check it to verify that it's correct, okay? And then here is how we sample. So hand and then the left-hand arrow sample deck underscore DF $suits, and I'm going to draw 5 cards, right? And then what I'm going to do is I'm going to use the sum function here, right? Using the sum function to count up how many spades are in this hand that we drew using sample. All right, and we're displaying the hand so we can see the number of spades and then what values are in this hand variable, right? So let me erase the marks there and run that, and boom, you see the cards we've drawn were diamonds, clubs, spades, diamonds, spades. So that is 2 spades, which is shown right here. Hitting Control Enter as many times as I want, you can see that it is correctly counting the number of spades. In this case, 3. In this case, 3. In this case, only 1. So yes, this is working as we want it to. So now we need to change, right? If we're going to do a spades hand, we need to draw a 13-card hand. We're still summing the number of spades, so the second line doesn't change. We've just copy-pasted from above and changed the 5 to a 13. Okay, and run that, and you'll see, right, that we're drawing, and we can see 6 spades, and then 3 spades, 3 spades, 2 spades, 7 spades, a very good spades hand, generally speaking, right? So the problem here is that we can't really use the central limit theorem. Why? Well, our sample size is fixed, right? A spades hand has 13 cards, and I can't increase the sample size. So that leaves only the second lever of the law of large numbers. In other words, I can draw as many spades hands as I want. I can do millions. I can draw millions of spades hands and count the number of spades. All right, so I am allowed to use the law of large numbers as a lever to get increased accuracy. Okay, so these are some details from the PowerPoint, which you've seen. And what do we have here? Right, we see that the expected value for the number of successes, right, the number of spades hands, spade cards, drawn into a spade's hands is 3 1/4. All right, so what are we going to do? Well, we're going to take the HTML table that's in here, right, and we're going to fill in from the simulation the grand mean of the number of spades drawn into these hands. And we're going to do it for sample size 1,000, 2,000, 5,000, 10,000, 50,000, and 100,000. Okay, I will say that this is aspirational. Let me explain. We get a scrap of cloud computing given to us by the data hub, right? Do we have a ton of cloud computing power? No. We've got a little. And so 50,000 is probably fine. 100,000, we don't know. It might take 15 or 30 seconds to run. It might hang up, right? So at some point here, we're pushing. What we can do is we can run this on a local machine where we have a lot more power to give to R, right? But here we'll have whatever the cloud gives us. So I'm just going to say that hopefully we'll get here. And we'll be able to get it done, but there's no guarantees, right? At some point, we run out of computing power. And again, that's just a limitation of using R in the data hub, right? We just have a limited amount of CPU power. Okay, so we've taken the for loop from before that you've seen a lot of times, and what have we done? We've changed to where we draw a hand of 13 cards, and then we put the number of successes into the num_success vector. Notice that we create the num_success empty vector. Number of samps is 1,000, so it's going to run the for loop 1,000 times. This is cool, right? This allows us to change things really easily. We've got a title down here that says histogram of spades, hands drawn equals 1,000, so we can update our title to make things easier. We're also doing the blue lines at the 5th and 95th percentiles. Okay, so run that. And there you go. You can see that the number of spades, it is a nice bell-shaped distribution, right? With a longer tail to the right and a shorter tail to the left. But the values, most of the values are piling up in that 2, 3, 4 range, and that does make plenty of sense. So we'll take this grand mean of 3.252 and go back to our table and put it in the second row, right? So right in there. And we can do the exact same thing a couple more times, right? So we're going to copy paste this loop, and we're going to change this to 2,000. And so we're going to change the title to 2,000, and we run it. Okay, now notice, and by the way, I can change the breaks equals. Notice that I have it at 8. I can set that a little higher. Let's say breaks equals 12. This doesn't do any better, so I'm going to go back, maybe try breaks equals 10. Okay, so 8 or 10 seems to be the best. Notice the blue lines at the 5th and 95th percentiles. Again, the data stacking up here in the 2 to 3 range. Okay, and of course our grand mean estimate is 3.197. And we're going to copy paste that value. Copy, go back here, and right here, I believe, yeah, for the 2,000 trials, right, that was our grand mean. So you can see our exact value is 3.25. That's the theoretical value. That's what we're trying to estimate. All right, so we're doing better. Now we've got to do 5,000, so I'm going to copy paste and change this to 5,000, change this to 5,000. I'm going to try breaks equals 12. I don't know what will work well. Again, we're getting this thing spaced out, so let me try breaks equals 10. Breaks equals 10 seems to work well, so for 5,000, wow, we're getting really close to 3.25. And so we'll put it in here. For the 5,000 trials, 3.254. And again, you can see what's happening, right? That as we go down, hopefully this value will become more and more accurate. Also, if you look, what we're hoping is that the blue lines showing the 5th and 95th percentile, hopefully they'll get a little closer together. We're looking for a narrower and narrower bell curve, but the law of large numbers doesn't force a narrowing of the bell curve necessarily. So we'll just have to see if that gets any better. So that's 5,000, and I'm sorry, I've got to go back up to the table. 5,000, 10,000, 50,000. Okay, so let's do that. Let's get this one set up for 10,000. And then the one below it will be set up for 20,000. Okay, and let's run it and run it. All right, and notice that the blue lines are not getting closer together. We are getting a nicer bell shape as it goes. For the 20,000 hands drawn, we have a 3.2669. So that's for 20,000. Oh, we weren't supposed to do 20,000. We're supposed to do 50,000. Okay. Oops. I'll have to go back. So I want to do 10,000, which is 3.2386. For 10,000 is 3.2386. And then for 50,000, okay, so after our 10,000, we come back down here. After 10,000, we're supposed to do 50,000. So I'm changing those and running it. And 50,000 is not taking that long. And so, wow, 3.24988, that's pretty close to the value we're looking for. And it should be noted that what are we doing? We can calculate the expected value theoretically here. So if we know the value that we're looking for, we're targeting, right? That's the whole thing. We're using the law of large numbers to estimate this value. It just so happens that we know the actual value we're trying to estimate. So we can see the accuracy of the estimates start to improve. Okay, and we just need to finish this for 100,000. Now the 50,000 ran pretty quickly, so I'm hopeful that for 100,000 this will be also easy enough. And again, I'll try breaks equals 12. I don't know what number of breaks will work. And it ran it pretty quickly. Breaks equals 12 works well. The blue lines have not moved, but the bell curve is getting more bell-shaped, more symmetric and bell-shaped, better defined. And again, with tons of the values piling up here around 2 and 3. Okay? So take the 3.25138 back to the table. And again, we know the actual expected value. This was calculated theoretically. Okay, so we can see what we're trying to do, right? We're hoping that our estimates get closer and closer and closer. And we're not hoping, but the law of large numbers says that our estimated values will get closer and closer and closer to the actual value, right, as the number of repetitions increases, the number of, not the samples increases, but the number of samples. The number of times we draw a sample here, not the sample size, but the number of samples increasing. Okay, and you can see that in this chart, all right? And by the way, your values may be different. It's a randomization function, so therefore are your specific values in this column going to be exactly identical to what I saw? No, of course not. You're going to get a similar set of values, though, and you should fill those in. All right, so that's the hypergeometric distribution applied to the game of spades.